Today in the workshop, we're testing cases for the Raspberry Pi 4. We'll see how to assemble 6 enclosures and then we'll test them for heat dissipation and Wi-Fi performance. We're making our case today, so welcome to the workshop. Well, hello and welcome to the workshop, and today in the workshop I'm going to be evaluating the performance of a number of different enclosures for the Raspberry Pi 4. Now you might think, well, what is the big deal? A box is a box. All you need to do is put your Raspberry Pi into a box, seal it up, and make certain that you can connect things to it. Well, there is a bit more to it than that. The case can actually affect the performance of the Raspberry Pi, and depending upon the application you have for your Raspberry Pi, it can make a very big difference in the success or failure of your project. Now, a Pi can be used for a number of different applications. You can use it as the center of a home security system. It can be an IoT device. It can be a multimedia center. And all of these different applications have different requirements, and you need to select a case that will suit those requirements properly. Now, I'm focusing today just on the Raspberry Pi 4, but of course there are cases for all the different models of Raspberry Pi. The 2B and the 3B can use the same cases. The 3B Plus has a power over Ethernet connector, so it needs a slightly different case. And of course the Raspberry Pi Zero is unique in itself. But today I'm just focusing on the Pi 4 because it is the most recent model and also is the model that dissipates the most heat, which is one of the factors we're going to be taking a look at. So what I want to do now is just show you what the requirements for a Raspberry Pi 4 case are. We're going to look at evaluating these cases using some software, so there is some software we'll be working with today, and then I'll show you a number of different Raspberry Pi 4 cases that I'll be using today, and we'll check them out, and from this you can determine which would be the best case for your Raspberry Pi 4 project. There are a number of considerations when choosing a case for the Raspberry Pi, and there are many custom enclosures available. Of course, you can always make your own case. Just remember that the Pi uses 2.5mm hardware as opposed to the more common 3mm hardware. However, 2.5mm hardware is quite easy to find. The majority of Raspberry Pi cases are made of plastic, acrylic, or aluminum, although you will sometimes find other materials used as well. Many of these enclosures have integrated fans. Some of them have integrated heat sinks, and some have both fans and heat sinks. The enclosure can affect the performance of your Raspberry Pi. With that in mind, we need to evaluate several parameters when testing a case for the Raspberry Pi. One of the most important parameters when checking a Raspberry Pi case is thermal dissipation. The Raspberry Pi gets very hot and will go into CPU throttling if it runs too hot. There was a firmware update in late 2019 that can improve the thermal dissipation performance. You can apply passive cooling by adding heat sinks to the Pi. You can also apply active cooling by using fans. Both a fan and a heatsink can be combined for additional cooling performance. There are also more exotic forms of cooling such as liquid cooling, but we won't be covering that today. The Raspberry Pi 4 has both Bluetooth and Wi-Fi. The antennas for these are on the circuit board. They're actually underneath the circuit board on the Raspberry Pi 4. Using a metal case can block the signal and reduce the Wi-Fi and Bluetooth performance. Another consideration when choosing a case for the Raspberry Pi is access to the various connectors which you may need in your project. The first and foremost is the GPIO, or General Purpose Input-Output connection. There is also the PoE, or Power over Ethernet connection. On one side of the unit, there is a connection for a touchscreen display. Underneath the board, you will find access to the micro SD card that serves as sort of a hard drive for the Raspberry Pi. There is, of course, the power connection, which in the case of the Pi 4 is a USB-C connector. There are two HDMI outputs in the form of micro HDMI connectors. There's also a CSI connector for a camera, and a 3.5mm jack for audio-video output. On the other side, there is an Ethernet connector, two USB 3 connectors stacked upon each other, and two USB 2 connectors also stacked upon each other. These are all considerations when choosing a case for your Raspberry Pi. Now these are the cases that I'm going to be using today with the Raspberry Pi, and I will be assembling these and running them through all of our various tests a little bit later on in the video. I just wanted to show you what we were working with today. Now the first one is the official Raspberry Pi case from the Raspberry Pi Corporation, and it's a very simple plastic case, very inexpensive and commonly available in the official red and white Raspberry Pi colors. The other one is a designer case called the Argon 1 Pi 4 case, and this case is very highly rated. It is made of aluminum and it has integral heat sinking and is going to be a very interesting case to test. This would be a very nice one for a media center because of its appearance, in my opinion. This is the Eleduino case, and this is an aluminum case. It's an aluminum alloy case for the Raspberry Pi. This one from Pimoroni is a heatsink case, and this actually encloses the entire circuit board in one massive heatsink, which should really aid the heat dissipation, but of course I'm curious to see what that does to the Wi-Fi signal. This one over here is the GeeekPi case. It's a plastic case. And this one over here from a company called Smraza, I'm hoping I'm pronouncing that right, comes with a lot of things. It's a plastic case. It also comes with a fan and even includes a power supply for the Raspberry Pi. And this is a small sampling of the number of cases that you can get for the Pi 4, but I think because of the various designs of these cases, it'll give us a good idea of how the Pi performs in the different types of enclosures. Now, in order to make sense of the tests that we're going to be doing, we need to establish a reference point, and so this is my reference point over here. This is a Raspberry Pi 4 with 2 gigabytes of RAM. There is, of course, also a model with 1 gigabyte and one with 4, but I decided to choose the 2 gigabyte one because it's sort of middle of the road, and it's also a very popular model, especially as last month the Raspberry Pi Corporation had a temporary sale where they placed these on at the same price as the 1 gigabyte one. Unfortunately, that sale is over right now, but I did manage to grab a few of them while they were on sale. Now, as you can see, my setup here is very basic. I've got the Pi 4 sitting on a mouse pad, which is how I usually experiment with things on my workbench. I like the mouse pad because it tends to grip the printed circuit board a bit so it doesn't move around, and of course it also insulates it, which is very important for the bottom of the board. Now, I've got attached to it just a standard USB mouse and a USB keyboard over here. You'll also notice that I've got an Ethernet cable attached to this. The purpose of that will become apparent a little bit further on in this video. This connection over here is the micro HDMI connection, which is just going to an HDMI monitor. I'm only using one monitor for these tests, and this is the USB-C connection for the power supply. And so that's the base that we are going to be referencing everything by. We were going to take measurements of temperature, and we're going to take measurements on the Wi-Fi using this and then compare those measurements to the results we get when we place this Pi into an enclosure. And I'm going to use the very same Raspberry Pi that I'm using for all of the enclosures so that we have something that's constant and I don't have a variance between the two different Pis. Now, this is a very recent model of the Pi 4, so it has the latest version of the firmware, because in 2019 they did update the firmware in order to try to reduce some of the heat dissipation. It's also got the latest version as of this recording of Raspbian, which was released in February of 2020. Alright, so now that we've seen the criteria we're going to be testing for, and you've seen my base test setup, it's time to start the tests. And the first test I'm going to do is going to do with heat dissipation, because of course this is a very important factor. Now, in order to test heat dissipation, I'm going to be using a utility called Stressberry. Stressberry is a utility that performs a stress test for the Raspberry Pi. Stressberry tests the core temperature of the Pi under different load conditions. The utility runs under Python 3.6 or higher. Stressberry produces a plot that can be saved as an image file for future reference. So let's use Stressberry to test the heat dissipation of our Raspberry Pi. Now, Stressberry is a Python program, and we're going to run it at the command line of our Raspbian operating system. But before we do that, we need to ensure that we are running version 3 of Python and not version 2. Now, the Raspbian operating system, which we're using on the Raspberry Pi, comes with both version 2 and version 3 of Python. And by default, it will be running version 2 at the command line. You're going to need to make some changes in order to make that version 3 by default. Now, if this is a Raspberry Pi that you've been using for other operations, you may have already done this. And the way to check is to go and type in Python, and a space and 2 dashes, and then version. And as you can see, I'm running Python 3.7.3, so I'm fine. But if you come up with a Python 2 version, you're going to need to modify a file in order to always load Python 3 instead. Now, the file we're going to modify is the bashrc file, and so we're going to need to edit that. So we'll use the nano editor, and then a space, and then a tilde and a slash, and then dot bashrc. Don't forget the period at the front there. And this will bring up the file in the nano editor. Now scroll down to the very bottom of this file. Now, I've already added this line over here, but this is the line you're going to need to add. Alias Python equals, and then USR bin Python 3 enclosed inside 2 brackets. Now that needs to be added to this, and then you'll do a Control X to get out of here. Now, if you've modified the file, you'll be prompted to save it, and you need to hit a Y to do that. Obviously, I don't need to do that because I've already done this. Now, after you do that, you're going to need to reboot your Pi in order for this to come into effect. And now we can install Stressberry. Now, Stressberry is a Python program that invokes another application called Stress, which you need to install first. And so you can do a sudo, and that's actually optional. I think you actually don't need to really do the sudo, and then apt install and stress. Now, in my case, of course, I've already done this. It's already at the newest version, but if you haven't done this before, it will install. And now we can install Stressberry. Now, Stressberry is a Python package, and so we are going to use pip, which is the Python package manager. However, since we're using Python 3, we're going to use pip 3. So the command is pip3 install Stressberry. And again, I've done this already. And it says the requirement's already satisfied. In your case, that would just install Stressberry. And then after that, I would recommend that you restart your Raspberry Pi again, and we can run Stressberry. So now I'm going to run Stressberry on my Raspberry Pi that is sitting here naked on my workbench. And again, this will be my base test. And so I'll use the results of this to compare to the Raspberry Pi in all the various cases. Now, Stressberry takes quite a while to run, so I'm going to start it running. I'm going to skip ahead so that you don't actually have to wait the full 8 minutes that it takes to run this test. Now, in order to run Stressberry, we do Stressberry-run, And then we have to give it the name of a file that we are going to place our data into it. I'm going to call mine base1.dat. It's advisable to use the .dat extension. And then just hit enter. And it's going to start by looking for a stable baseline temperature. After that, it is going to run it in an idle mode for a while, and then it is going to stress the CPU by running all 4 cores at a very, very high rate. And it'll display the frequency that it runs at while it is doing this. And now it's found its baseline temperature, and it is going to begin the tests. Again, I'm going to skip ahead so you don't have to actually watch the entire thing proceed. And now we are actually beginning our test. It is going to idle for 150 seconds, and then it is going to stress all 4 cores for 300 seconds, or 5 minutes. And now it is beginning to stress all 4 cores of the CPU. And you'll notice the temperature increasing during this phase. And now it has run its test and is going to idle again for 150 seconds. And we should see the temperature fall. And there we go, we finished with Stressberry. Now what we can do is we created the DAT file and it's in our home directory. So let's go and take a look. We only need one of those, Bill. And there it is, base1.dat. And we can open that with a text editor. And as you can see, it has captured all the data, but as you can see, the data that we've captured is a little bit difficult to interpret. Well, there's a way around that, and that's to do a Stressberry plot. And so we do Stressberry-plot, and then the name of the file that we are going to use as the input, which in our case is, and then a -O for an output, and the name of a PNG file. We're going to call it and we'll run that. And it's run. And now we have a PNG file. And as you can see, the PNG file is much easier to interpret the data. We can see when we idled at the beginning, and we see how our temperature on the stress at the maximum came above 80 degrees Celsius, and then afterwards how it dropped off. And so we will repeat this experiment for the Raspberry Pi in all the various cases and compare it to this one, which is the base one without any case at all, and we'll see how it does. Now, another important aspect of a Raspberry Pi case is, does it affect the Wi-Fi and Bluetooth performance? Does it attenuate the radio waves? If the case is made of metal, there's a good chance that it's going to block the radio waves or severely reduce them and therefore impact the performance of both the Wi-Fi and Bluetooth. Now, your application may not even need Wi-Fi and Bluetooth, and if that's the case, then you don't have to worry about it. But if you do, you're going to need to know that the case that you've chosen will indeed allow these radio signals to pass through. Now, what I'm going to be using in order to evaluate this is a utility called iPerf. Let's take a quick look at iPerf. iPerf is a tool for measuring the bandwidth on an IP network. Using iPerf requires 2 computers, one acting as a server and the other as a client. One server computer can host an unlimited amount of clients on the same network. iPerf is an open source utility and is available for virtually every platform, including Windows, Mac OS, and Linux. iPerf was developed by ESNet and Lawrence Berkeley National Laboratory. So let's start using iPerf to test the network performance of our Raspberry Pi. Now this is the iPerf homepage at iperf.fr, and this will give you pretty well all of the information that you'll ever need about iPerf. You may also need to go to this page to download iPerf onto another computer if the other computer is not a Linux computer. Remember, you're going to need an iPerf server as well as an iPerf client, and in our case, our Raspberry Pi will be the client. If you need to install it on a Windows or Mac machine, what you need to do is go to this download iPerf binaries, where you will find links for virtually everything: Windows, Androids, iPhones and iPads, Mac OS X, etc., etc. You don't need to worry about it through Ubuntu and Debian, etc., because you can install it at the command line the same way you do on a Raspberry Pi. On a Raspberry Pi, all you need to do to install iPerf is just type in sudo apt-get install iPerf, and that will install this onto your computer. Again, if you're using a Linux machine, such as an Ubuntu machine, as I'm doing for your iPerf server, this is also what you'll need to do on the server side. In order to run our iPerf test, we're going to first need to set up our iPerf server, which is quite easy to do. The first thing we're going to do is open up the terminal and go to the command line. And before we do this, let's just go and take a look at some of the options we have for iPerf. So just type iperf and then a space -help to get the help screen. And I'll scroll up on this. And as you can see, there are a wealth of options over here for iPerf. Now, we are going to use it very basically. iPerf/s is going to be the server, and on the other end, iPerf/c, and then the host address will be the client. And it's really all we need to know, but I just wanted to point out that there are a lot of tests that you can run using iPerf. Now, we'll go back down over here and clear our screen. And before we start off and run iPerf, we need to know what the IP address of our server is. So let's do an ifconfig. And that will give us back a number of pieces of information. The key one we want is our IP address, which in my case, 192.168.1.129. Now obviously when you run this, you will get a different address. And now we can just run iPerf. So iperf space -s, because we're going to run it as a server. And it says the server is listening on TCP port 5001. And so let's remember our IP address, 192.168.1.129 in my case, and go over to the Raspberry Pi, which we will use as a client. Now we are back on the client side, on the Raspberry Pi side, and this is our Raspberry Pi bare board that we're using as a reference point. Before we run iPerf on this, though, I want to show you another command that you can use to test the parameters of your Wi-Fi network. And you see it right now on the screen, sudo iwlist WLAN 0 scan, and WLAN 0 on the Raspberry Pi is the Wi-Fi network, and this will scan for all of the Wi-Fi networks and give you back a wealth of information. In fact, it's kind of like information overload. So let's just load that, give it a second, and it comes back with a lot of information. Let's scroll up and see what we've got over here. Now, obviously, a lot of these parameters are things that we aren't going to be needing, but we can get a lot of information. For example, this particular network here, WJNet24_EX, is a Wi-Fi that I have upstairs in my house on the second floor. I've got Wi-Fi on both the second floor and down here in the basement. It's a 2.4 gigahertz Wi-Fi. It's showing me the quality and the signal level of that, and that's really the parameter that I want to get, the signal level and the quality. And I can scroll down and see that for all of the various networks that are available to me, the ones in my home and some of the ones that are in my neighbors' homes. And these parameters can be very useful, especially when you're also considering the Bluetooth, because we aren't going to be testing the Bluetooth, but the Bluetooth also uses a 2.4 gigahertz band, and so the performance should be the same. So I'm going to run that for each one of the cases that I put the Raspberry Pi in, just to get some numbers, and this will be our base number that we have over here. Okay, now we can run iPerf. Now you recall we set iPerf up as a server on my Ubuntu machine, and that my server address was 192.168.1.129, so we do iPerf space -c because it's going to be a client, and then a space in the IP address of the server, 192.168.1.129. And we'll enter that, and it's connected. We'll give it a moment to get some parameters. And these are the parameters you come back with. Now, this base test was done with the Ethernet connection, and that's why I had the Ethernet cable in my Raspberry Pi. So this is about the best performance I'm going to be able to get right now. It is not the Wi-Fi I've just tested. And as you can see, I'm getting 823 megabits per second on the Ethernet right now. And so what I'm going to do is I'm removing the cable from the Raspberry Pi, and so now the Pi is going to be forced to be using Wi-Fi, and I'm connected to the 5 gigahertz network right now, and I'm going to perform all my tests on the 5 gigahertz network because I will assume that you are going to likely use the 5 gigahertz network if you're building something like a media server. Now keep in mind though that the signal strength in the 5 gigahertz network is often lower than it is on the 2.4 gigahertz network, and for a reference, I'm approximately 8 meters or 26 feet away from my router, and there are a number of walls between me and the router. So let's go and rerun that command. And we get our results back. And as you can see, the bandwidth is quite a bit reduced from what it was earlier. This is what I had on the Ethernet, and this is what I had on the Wi-Fi. And we're going to run this for all of the different enclosures and see how this compares to this reading, because this is our base reading, and I'll tabulate all of those so we can take a look at them at the end of the video. And so now we've arrived at the moment of truth. How did these different enclosures perform under our tests? How did they work with Stressberry and iPerf? How easy were they to assemble? And did they give me access to things like the GPIO and the camera connector? So without further ado, let us go and take a look at the results of all of my tests. Before we examine the results I received from testing the various enclosures, let's take a look at the results from the base test. This is the test with the Raspberry Pi just sitting on a mouse pad without any heat sinks or fans attached to it. Now, as you can see from the Stressberry data, the Pi was idling at approximately 53 degrees Celsius. When the stress was applied, the temperature went up to about 83 degrees Celsius maximum. After it started its cool down period, the temperature fell to about 60 degrees Celsius. Now for the performance, the 2.4 gigahertz signal had a level of negative 55 dBm and a quality of 55 out of 70. The 5 gigahertz signal had a level of negative 73 dBm and a quality of 37 out of 70. And the iPerf bandwidth test gave a result of 90.9 megabits per second. And we can use these results to compare to the other enclosures. The official Raspberry Pi case is made of ABS plastic and is probably the simplest case to put together. You literally just drop the Pi into the bottom of the case and snap the top on. Now it has access to all of the various connectors, including the micro SD card. If you want access to the GPIO, the camera, and the display and power over Ethernet connectors, you can take the top off of the case. You could install a hat on this device with the top off as well. Now I tested the official Pi case with the top on, and as we can see from the Stressberry data, it idled at a higher temperature than the naked Pi did, approximately 63 degrees Celsius. When we put the stress on it, it went up to a maximum temperature of about 83 degrees and then dropped to a temperature of about 68 degrees Celsius in the cool down period. Now, performance-wise, the Wi-Fi signal at 2.4 GHz was negative 58 dBm, and its quality was 52 out of 70. The signal on 5 GHz was negative 69 dBm with a quality of 41 over 70, so this is actually better than the naked Pi, probably because it raises the board slightly and the antenna is on the bottom of the board. That also showed up in the iPerf test, where I got a bandwidth of 95.1 megabits per second. The Pimoroni Heatsink case literally encases the Raspberry Pi within a large heatsink, and it is very simple to assemble. The device consists of just two pieces, the top of the heatsink and the bottom. Before you assemble it, you need to attach some thermal pads onto the top. The thermal pads have an adhesive, and I found the adhesive a bit difficult to work with, but otherwise assembly was quite easy. You lay the board down onto the top piece and then assemble it with 4 screws. The screws have Allen heads, and an Allen key was provided to do the job. There are openings in the case to allow access to the camera and display connectors as well as the power over Ethernet, and the case is notched for easy access to the GPIO. Once I got the case together, I ran Stressberry, and as you can see, the results were very impressive. The Pi idled at about 37.5 degrees Celsius and then achieved a maximum temperature of about 53 degrees Celsius. Very impressive. After it went to the cool down period, it dropped to about 46 degrees Celsius. Now for the data for the Wi-Fi signals. The 2.4 GHz was at negative 64 dBm, a notable reduction from the naked Pi. The quality at 2.4 GHz was 46 out of 70. At 5 GHz, the signal was at negative 72 dBm and the quality 38 out of 70. This is about equivalent to the naked Pi, meaning it attenuated more at 2.4 GHz than it did at 5 GHz. The iPerf running at 5 GHz was an impressive 92.3 dBm. The GeeekPi case is made of ABS plastic and consists of 3 main pieces: a bottom plate, a side, and a top plate that is removable and also has a fairly large muffin fan on it. I assembled the case quite easily and then attached the muffin fan to the 5-volt supply on the GPIO. The fan will be on all the time. You can also attach it to the 3.3-volt supply if you want to run it a little quieter, but I decided to give it the maximum performance at 5 volts. Now, as we can see from the Stressberry data, the performance was very good. The idle was down at an incredible 36 degrees Celsius, and when it was stressed, it went up to a maximum peak of about 55.5 degrees Celsius, which was quite impressive. After cool down period, it fell to a very impressive 40 degrees Celsius. So this is excellent data as far as thermal dissipation goes. Now, as for the Wi-Fi performance, at 2.4 GHz, I got a signal of minus 50 dBm and a quality of 60 out of 70, which was very impressive. I also, at 5 GHz, got a negative 74 dBm and a quality of 36 out of 70, which is very close to the naked Pi. The data transfer rate on iPerf was also quite impressive at 92.2 megabits per second. About the only fault I would give this case was the noise of the fan. It made a high-pitched whine, which I found quite irritating. And of course, the fan is on all the time. It is not controlled by the temperature. It is on as long as power is applied. But other than that, this case worked very well with my Raspberry Pi. The Eleduino Raspberry Pi case is made of aluminum and consists of a bottom plate, a top plate, and 2 side plates. These are all fastened together with screws that are provided, and a small fan is also provided, which is attached to the 5-volt line on the GPIO. There is no access to the GPIO available on the case, but there is a small slot on the side so that you could attach a ribbon cable and get access to the GPIO pins. Access to the camera and the display would not be possible with this case. When I went to test this case, however, I ran into a major problem. When inserting the HDMI cable into the micro HDMI slot, I could not make connection. The cable would not go in deep enough because it was being blocked by the case. Thinking that this might be my cable, I tried 2 other cables from 2 different manufacturers, plus an HDMI to micro HDMI adapter, but I had the same results. The case was simply blocking the connector from being able to be used properly. For this reason, I was unable to gather any data for this case. Now, granted, I could have SSH'd to the device and done it that way, but I felt that that was unfair because the other cases were being tested with a local HDMI monitor. So I was not able to get data for the Eleduino aluminum case. The Smraza case for the Raspberry Pi 4 is a very interesting design. It consists of a number of acrylic layers that you literally sandwich the Pi into. The case comes with a number of small heat sinks, as well as a power supply that had a power switch, so this is really a complete kit for getting your Raspberry Pi up and running. I found the assembly to be a bit difficult, and if I had to do it again, I would temporarily insert 2 of the corner screws upside down in the case so that I could align everything while I was layering it. But once I got it all layered, it seemed to fit together fine. It comes with a small fan that attaches to the top of the case, and like the other case that uses a fan, is permanently attached to the GPIO on the Pi. It can be attached to the 5 volt or 3.3 volts. I used the 5 volts so I would get maximum cooling. Now, looking at the Stressberry data, you can see this is also a very impressive case. It idled at about 36 degrees Celsius and achieved the maximum temperature under stress of a little over 52.5 degrees Celsius. The cool down brought it down to about 37.5 degrees Celsius, so this case has excellent thermal performance. As for RF performance, it was also very impressive. The 2.4 GHz signal level was negative 54 dBm with a quality of 56 out of 70. The 5 GHz signal was at negative 72 dBm with a quality of 38 out of 70. And the data transfer rate for iPerf was 93.4 megabits per second. I'll also note that the fan on this case, although it runs all the time, is extremely quiet, and I would have no problem having this case next to me all day if I was using the Pi as a personal computer. The final enclosure I tested for the Raspberry Pi 4 was the Argon 1, and this case is literally in a league of its own. It's much more expensive than the other cases, but that shows in the quality of the case. It consists of a top piece that has a circuit board and a fan already installed on it. There is also a second circuit board that comes with it to route the HDMI and audio connectors out to the back of the case. The assembly of the case I found to be a little bit difficult. You put some thermal pads onto the top piece and then insert everything and screw it in. And this is the problem that I had, was trying to align everything up so that the GPIO would connect to the connector on the top. I had to struggle with this quite a bit, but I eventually got it in. After that, you put the bottom plate on, and that is made of plastic, and I assume it's constructed of plastic to allow for the Wi-Fi and Bluetooth to work a little better, as the antennas for those are underneath the board. The case also requires some software to be installed, and there are instructions that come with it. This is software that will allow the fan to be controlled and also to allow the power switch to have a number of functions such as standby and reset. This is the only case I reviewed that actually had a power switch, and it would be ideal for using the Pi as a personal computer. Now, testing it was wonderful. The test on Stressberry, as you can see, it idled at a temperature of about 37 degrees Celsius and achieved a maximum temperature of a little under 50 degrees Celsius and then went down to idle at about 43 degrees Celsius. I never got to test the fan noise because the fan is a variable speed and at 55 degrees Celsius should come on at 10%, 60 degrees Celsius should come on at 55% and should be at 100% when it achieves 65 degrees Celsius. But as you can see from Stressberry, I never achieved those temperatures, and so the fan never came on, and I was unable to evaluate fan noise. Now, the RF performance of this case, however, was a bit poor, and that was probably because of the all-metal construction, even though it does have a plastic bottom. For RF performance, I got negative 69 dBm on the 2.4 gigahertz signal with a quality of 41 out of 70. The 5 gigahertz was a little bit better at negative 79 with a quality of 31 over 70, but at 5 gigahertz my data transfer rate was only 68.5 megabits per second, which was the poorest rating of all of the cases. However, if RF performance is not important to you, this would be a superb case for your Raspberry Pi 4. So let's summarize the results of our testing. I've got them all here in a table so you can compare everything. Now first let's take a look at the first 3 columns, which have to do with thermal dissipation. And as you can see, the majority of our cases handled this very well. And also during the tests, I did not observe any CPU throttling. The Pi by itself on a mouse pad in the official Pi case, however, did not handle this well. In fact, the official Pi case made things worse than by just putting it on a mouse pad, which makes sense because it's essentially a box that enclosed the Pi and trapped all of the heat. Now you could improve upon this case, of course, by taking the lid off, and you could also add some small heat sinks as the GeeekPi and the Smraza case had, and that would probably improve the performance of that case. However, I would not be using the official Pi case for anything that involved performance. On the other hand, the official Pi case was one of the best ones with 5.0 gigahertz Ethernet and was the best iPerf data transfer rate. So for an IoT application or something where you did not use high performance but needed good data transfer or needed wireless, this still could be a good choice. In terms of the wireless, most of the cases handled it quite well. The biggest surprise was the Pimoroni Heatsink case, which actually did very good on the 5 gigahertz side. However, you'll notice the Argon 1 case, which totally sealed it up except for a plastic bottom, did not fare that well at all, and I think that is because of the metal case. Now, as for the Pimoroni Heatsink case, one explanation I have for it doing so well despite encasing everything in metal is that that case is not grounded, and so it just surrounds it. And this is just speculation, but it's possible that at 5 gigahertz it was actually acting as an antenna. You can also see it got a very good iPerf data transfer rate, as did everything except the Argon 1 case. The Argon 1 case was quite impressive though, because although it has a fan, it never got hot enough to activate it. And of course the Eleduino case I have no data for because I was unable to plug in the micro HDMI connector. Now I could have used a remote SSH and performed all of these tests, but it was my feeling that if I couldn't do that, that it wasn't suitable for these testing. However, in an application where you don't need the HDMI, it could still be a consideration. It was a good metallic case. So all in all, these are the results of the cases that I tested for the Raspberry Pi 4. So as we've seen, there are a variety of cases we can use for our Raspberry Pi 4, and each one has specific advantages and disadvantages. Most of them are very good on heat dissipation, except of course for the original Raspberry Pi case, but even that has its own uses. For example, if you're using a Raspberry Pi on the workbench, you might want to use that case with the top off so that you can get at all the GPIO pins and protect the Pi a little bit more if it happens to get moved around the workbench. It is a very easy case to put together. You literally drop the Pi into it and you're ready to go. Now, if I had to choose a favorite case here, I would say hands down it is the Argon 1. Mind you, this is the most expensive case I evaluated, but not only did I like the looks of it, I liked the way they brought the GPIO out to the back of it with the color coding on the GPIO pins. That was even neater. I liked the way all of the connectors are on the back side, and I especially like the power switch that they included with it. It's actually an intelligent switch that can not only power down the unit, it can also put it into standby or do a reset by pressing it differently. It also was obviously an excellent design in that it didn't even get hot enough during the Stressberry test for me to even find out if the fan was making any noise, because the fan didn't even turn on. Now, if you want a case that has a lot of the advantages of that, but you don't want to pay the high price, after all, the Argon case is more than half the price of the Pi itself, then I think the Smraza case is very nice. Now, it was a little difficult to get together, as was the Argon case, and you may or may not like the design of the layered acrylic, but if you do like that design, it had excellent thermal capabilities. It also had really good Wi-Fi and Bluetooth capabilities, and of course it had a little fan inside it that I could hardly hear, so it was very silent. It would also make a good case for something like a personal computer, especially because it came with a power supply that had an on-off switch, which is one feature I really wish the Raspberry Pi had. But all of these cases have their merits, and of course there are other cases. There's another popular case called the Flirk, which I did not evaluate because I simply don't have one, but I've heard good things about that, and there are dozens of other ones. So I'm certain that armed with the information I've given you here, using tools like Stressberry and iPerf, you can check out the cases. Now, on the subject of iPerf and on the readings I got from my Wi-Fi, you should remember that these are unique to my own situation here in the workshop with my router in another room in the basement, and of course if you tried it at home you would get different readings. But I think what you need to look at is, instead of looking at the actual readings, is look at how they compare to each other, and in that way you can judge which case has better performance in the Wi-Fi end and also the Bluetooth end, because Bluetooth will be using the same 2.4 gigahertz band as the lower Wi-Fi does. So with that, I'm hoping that you can select a good case for your Raspberry Pi. Now, if you'd like more information about these cases that I've used today, or you want to go over the data a little further, there is an article on the dronebotworkshop.com website, and you'll find a link below the video to that article. You'll also find a link to the DroneBot Workshop forums, which is a great community of people just like you who love electronics, who like to work with Raspberry Pis, Arduinos, NVIDIA Jetsons, ESP32s, and all sorts of fun things. And if electronics is your bag, well, then that's the place you want to be. The forum is free to join. Just send an email to forum@dronebotworkshop.com. Let me know what username you want. Give me at least your first name and a little reason why you want to join the forum. And we do that because initially we had some spammers, and this is our way just to get rid of them. So you'll also have to give us a day or two to get your forum application processed and give you an account. But once you're in, it's a great community to talk with. And finally, you'll also find a link below this video to join the DroneBot Workshop newsletter. It's not a sales letter. It's just my way of keeping in touch with you to let you know what is going on here in the workshop. And of course, if you haven't subscribed to the YouTube channel, well, what are you waiting for? All you need to do is click the subscribe button, and when you click that button, also click the bell notification, and that way you'll be notified every time I make a video. With the things that are going on these days, I'm going to try to get videos out as often as I can, but it's hard to keep a set schedule, and so this way you'll know first when a video has been released. So until we meet next time, please take good care of yourself and take good care of the people you love. We are in a very difficult time right now, but we will get through it by socially isolating and washing those hands. So take care, and I will see you soon here in the workshop. Goodbye for now.